So for this section, we are just talking about some specific types of Riemann sums. Remember, a Riemann sum is when we are approximating the area, or really we should specify the net area under a function or between a function and the x-axis by using rectangles where the height of the rectangle comes from the value of the function, and then delta x is the width of each subinterval, or delta xi is the width of each subinterval. Okay, remember that the height comes from, and this is just a typo, there should be a bar across that. So the height of each rectangle comes from the value of the function at the sample point, and the sample point can be anywhere on the closed interval of the subinterval, of each subinterval, okay? So specifically, we've got a few types of Riemann sums here. So a right Riemann sum is where the right value of each subinterval, or the right endpoint of each subinterval, is used as the sample point, okay? You really don't need to worry about this notation very much, but let me give you a visual because it makes a little more sense. So let's say that we have this interval and it's divided into, I don't know, 4 subintervals. So let's say this is x0, x1, we'll just do 3, that's easier, x2, and x3, okay? So we're dividing our subinterval like this. Remember, they don't have to be equal widths. For a right Riemann sum, the height of each comes from the right endpoint. So, well, that's not very straight. Okay, so I'm using the height at the right side of each subinterval to get the height of the rectangle. So we would do width times height, width times height, width times height, and then add all of those together for our approximate net area, okay, or area in this case, because those are all positive. For a left Riemann sum, we use the left endpoint of each subinterval. So I'll do roughly the same subintervals here. x1, x2, x3. Okay, so now the height of the rectangles is coming from the left side. Now, we could call this circumscribed or inscribed. The problem with that, though, is that if a function is not monotonic over an interval, so if it's not strictly increasing or decreasing, then just saying left or right endpoint doesn't guarantee that we're going to be circumscribed or inscribed. And so really, because we need to account for the possibility of a function both increasing and decreasing, it's better just to use either the left or the right endpoint to describe how we are finding the height of each rectangle, okay? This one right here is the midpoint Riemann sum, and here we're going to use the oops, didn't mean to do that. I've got some little lines on there, but that's okay. We're going to use the midpoint of each subinterval to get the height of the rectangle, so still using approximately the same subintervals as before. Now we would find the midpoint of the subinterval. So midpoint, remember, is the average of the two x values. So x0 plus x1 divided by 2 gives you this x coordinate. Okay, and then the height, if that's our sample point, height is determined by that. And then again, midpoint right about here. So the height of this rectangle is determined by the value at that sample point. And again, midpoint, looks like it's, yeah, there we go. Okay, so in this case, we have a little bit overestimate, a little bit underestimate, probably a little more accurate than just in the left or right endpoint, left or right Riemann sum, but this is the midpoint Riemann sum. So it takes a little bit more arithmetic to get to this because you have to plug in the midpoint values into your function to get the heights, okay? This last one is not specifically a Riemann sum because it is not based on rectangles, but it is instead based on trapezoids, okay? It is, however, a little bit more accurate than using just a Riemann sum. So here, every subinterval has 2 sample points, okay? Both the left and the right endpoints. So again, let me draw roughly the same subintervals here. Okay, so instead of using rectangles, we are going to use a trapezoid. And if you need to, turn your paper sideways or turn your head sideways, okay, because normally when we see trapezoids, we're used to the parallel bases being on top of each other. okay, something like that. But now they are going up and down because these are the parallel pieces. So the first trapezoid has one base that has a height of f of x sub 0, and the second base has a height of f of x sub 1, and then this is our trapezoid, okay? Area of a trapezoid is the average of the bases times the height. And then the second trapezoid, one base has a height here, base has a length, which is the height since we're going up and down. Okay, so trapezoid like that, and then lastly, right there. So you can see how a trapezoidal rule is going to be more accurate than either a left or a right or midpoint Riemann sum, because trapezoids are going to stick a little bit closer to the curve than a rectangle does. The thing about that, though, is you're also sacrificing some of your efficiency for accuracy, which when we're doing approximations, there's always kind of a balance between like how rough of an estimate do we need to be if it's going to be easier. So trapezoids are a little bit more complex as far as finding the area, but it's really not that bad, okay, because we can handle averages of bases and then multiply them times the height. Just remember, height goes this way when we're talking about trapezoid because it's the distance between the bases. Okay, so let's go through a couple examples. We have the integral from 0 to 3 of 1 plus x squared times dx. We have this definite integral, and we want to approximate its value using 3 equal subintervals, and first a left Riemann sum and then a midpoint Riemann sum. So for the left Riemann sum, I want to start by identifying where the ends of the subintervals are. I'm going from 0 to 3, and I want 3 equal subintervals. So I'm just going to make a table of values here, because actually this is going to be helpful for both part A and part B. So if I have 3 equal subintervals, and I'm going from 0 to 3, each one is going to have a width of 1. Okay, and I'm just going to make a table like this so I can keep track of my points. That one's pretty intuitive because a length of 3 and there's 3 subintervals. But remember, you can find the width by doing b minus a divided by n. So delta x equals 3 minus 0 divided by 3, so it gets us 1. Okay, so I'm going to go ahead and plug in the values here. So f of 0 is 1, f of 1 is 2, f of 2 is 5, and f of 3 is 10. Okay, that's just plugging those into the function f of x. So using a left Riemann sum, my first subinterval would go from 0 to 1. Okay, and so the height of the first rectangle is going to be f of 0. All right, so actually I don't want to write that as an area. My integral, 0 to 3 of 1 plus x squared dx, is approximately equal to a width of 1 times a height of 1 plus a width of 1 times, because this is the width of the second subinterval, and now we're using f of 1 as the height for the second subinterval or second rectangle, so 2, and then plus a width of 1 here times a height of 5. So we get 1 plus 2 plus 5, which is 8. Okay? Then for part B, now we're going to use a midpoint Riemann sum. So we're going to have to do a little bit more arithmetic than this. I'm going to make a table again. So the first interval is still going from 0 to 1, and then from 1 to 2, and then from 2 to 3. But now I need to know what f of the midpoints are. So I need to know f of 1/2, f of 3/2, and f of 5/2. So f of 1/2 is 1 plus 1/4, so that's 5/4. F of 3/2 is 1 plus 9/4, so 13/4. And then f of 5/2 is 1 plus 25/4, so 29/4. Okay? Now, delta x is still 1. The width of each subinterval is still 1. All right? We're just using different sample points to get the heights. Okay? So, and actually, since, yes, 1 times whatever is still just 1, but I am going to write the 1, but I'm going to factor the 1 to the front because I'm remembering that I do have to multiply by the width, but since it's the same on all of those, I'm showing that it's okay to factor that to the front. Okay, so then we have our first height, 5/4, plus second height, 13/4, plus 29/4. Okay, so it's going to be 1 times, and then the sum of all of these, which is 47/4.